Okay, thank you, Pierre. So I will try to convince you during this talk the power of using seismic arrays instead of single station. I must say that here I will speak out for Quentin and Ishao, who made essentially all of this work. And the entire project is actually in very close collaboration with Yehuda from USC, and also Dan Hollis and Frank Vernon from UCSD. And all the other people are from our group in Grenoble. So let's start with some basic observations of a seismogram, of a one-day seismogram, near one of the most active seismic faults in the world, the San Jacinto fault in Southern California. And a one-day seismogram, essentially in this location, will show earthquakes. So these are the peaks you can see on the plots. And this traditionally has been the kind of signal that has been used for seismologists for decades for monitoring seismicity along faults and locating and imaging fault planes at depth by picking essentially P and S waves. But you can see here that the seismic earthquake signal is actually a very small portion of the entire seismogram. And if we dive in and plot this trace as a spectrogram, as a clip spectrogram, you can see a wealth of interesting information on the continuous seismic data, starting with the low frequencies below 1 Hertz. So this is a spectrogram between 20 seconds and 20 Hertz. And from the below 1 Hertz, you see a very strong signal. This has been described for decades and understood as and mentioned as the microseismic seismic activity. And this is now pretty well modeled as ocean swell interaction that create variations of pressure at the bottom of the ocean. And this for different wavelength, both at low frequencies around 14 to 7 seconds. This has been mentioned as the primary and secondary microseismic peak. But also at higher frequencies, just below 1 Hertz, there's now also information that even what we call the wind-driven swell can also act as a strong source for generating seismic waves at higher frequencies that can propagate through the crust. This is pretty well modeled, as we have good information for the wind swell activity in the ocean and how it couples with the ocean bottom floor to generate seismic waves. But now, if we look at higher frequencies, above 1 Hertz, you see that the content of the wavefield is much more complex, with many transient signals, as you can see here, a very complex signature in the pattern. And most of this signal has actually been observed and understood as being local noise. And among this local noise, there is wind-driven noise, also probably car traffic in this location, and local engines, pump factories that can play a role, and also acoustic signals even in the higher frequencies that can be linked to airplane, helicopters activity. But here we are not specifically interested in this very local noise, but more to noise that is hidden in this data, and that comes from a distant location compared to the observation, and that can tell us some useful information about, for example, the nearby fault activity. And especially these type of data can be useful to extract tremor activity, both, of course, volcanic and non-volcanic tremors. These tremors have been shown to being correlated somehow with the activity of slow sleep events on faults that are extremely important in order to assess the full range of sleep on a fault. And especially it has been shown that this slow sleep hidden event can play a role in the triggering of very large earthquakes. So it's probably very important to better understand and characterize these tremors. Also, interestingly, there are some cases where tremors, non-volcanic tremors, were thought to be found, especially in Southern California near this San Jacinto fault, but were actually finally understood by especially Asaf Inbal that these tremors that really looked like non-volcanic tremors, they were associated with freight trains that generate very strong signal that can be recorded up to 100 kilometers from the railway, in this case in Southern California. These are typically very long trains that can be as long as 5 kilometers long and generate very powerful seismic waves, as shown here. And this tremor, again, very much look like a non-volcanic tremor. However, it has specific patterns in the spectrogram here with spectral lines that are associated with essentially the spacing, the even spacing between the wheels of the trains. And it's interesting to notice that in the recent years, this type of signal has been used for seismic interferometry, for imaging and monitoring purposes, and it's being used as a repeating very stable source. And also here an exotic example of type of signal, distant signal that you can find in the data above 1 Hertz, high frequency data. This is a very peculiar example. It's the case of a T wave, so very enigmatic T wave. So a signal that will be interpreted as that was actually also interpreted as a non-volcanic tremor. Initially, that very looks like a non-volcanic tremor that was interpreted as being associated with plate slip at depth. And actually, coming almost 1 hour after a main shock, a magnitude 7 earthquake in Japan, shown here. And it was actually finally discovered that this signal was related to a seismic energy that was transferred to the SOFAR channel in the ocean as an acoustic signal being reflected almost 1,000 kilometers away on the Emperor Simon chain, and was scattered back also as an acoustic wave in the SOFAR channel, and then being converted in seismic energy and recorded over the entire seismic network of Japan as this type of tremor. And actually, the seismic energy, acoustic energy, propagation is very efficient in the SOFAR channel. So there can be a lot of seismic observations that actually come from acoustic propagation in the ocean. So again, we are interested in discovering these distant signals that are hidden in the data. And because, again, local noise is very strong, we need to find a way to reduce the influence of the local noise and increase the influence of a distant signal, like a tremor, for example. So for this, we use seismic arrays, and that have the capability to decipher between different waves of different velocities and different azimuth coming on the array. And especially being able to decipher between rather body waves, like on this example with rather high velocities, in this case of 6 kilometers per second, and eventually what will be rather low velocity surface waves around, for example, 1 kilometer per second. So this is just a sketch showing an example of what will look like a beamforming analysis of this simple array with just a single source of body waves coming from distance. So now we have, of course, all our observations are more complex with local sources of noise, of surface waves essentially. That leads to a much more complex pattern in the beam forming plot here, which shows again body wave, but also a variety of wave packets arriving with slower velocities and different azimuth, and even in that case for sources that are within the array, this contradicts the plane wave approximation for the beam forming and generates even more noise in the beam forming result. So a simple way to proceed to remove the influence of surface waves and to keep mostly distant body waves is to mask somehow in the beamforming analysis, to mask the low velocity parts of this seismic data, and to keep only the distant high velocity body waves. So this strategy is applied here to the fold scan large N and long-term seismic array. So this is the first of its kind very long-term array observation located at the Pinion Flat Observatory here, close to about 20 kilometers from the San Jacinto Fault. It's composed of 300 three-component geophones as shown here, with continuous recording for 3 years. That is generating still, that will generate about 70 terabytes of data that will be available at the IRIS DMC. So there is again the sensitivity of these geophones are from essentially 8 seconds of period to 100 hertz in our case. So there's a wealth of data coming out from this type of observation. But here we will focus again on the idea of trying to extract distant tremor activity from this data. This is really the main scope of the presentation. So for this, we essentially follow the strategy that was shown in the sketch, but explain here. This is the map of all our 300 stations. Width is about 1 kilometer. So we take the raw data for each of these stations. 1 bit normalize the data to somehow destroy the amplitude information and essentially destroy the earthquake activity, because we want to get rid of the earthquake to emphasize the background, let's say, noise activity. And then we phase weight and slant stack all these data at different azimuth and at a velocity of 6 kilometers per second. So this essentially, going back to the beamforming plot, summarizes as keeping just one spot in the beamforming and going back in the temporal domain after slant stacking. And this is what this actually signal from one node looks like after performing this for one day. And you see that there is very different shape in the waveform from this trace compared to the initial trace that was extracted from one node. And then after this, to look at let's say, to search for tremor activity over long term, remember that we'll have almost 3 years of data here. We will compute the envelope of the signal and then median filter. This is very important, median filter over a window length of 5 minutes. And this is very important because, again, we want to get rid of the seismic activity and just keep the tremor activity. And this is the type of then observation we get over a long term. So again, we can perform this over a different range of azimuth. So here, remember, we are at the Pinion Flat Observatory. On one side, we have the San Jacinto Fault, and on the other side, we have the San Andreas Fault. So we can look at different azimuth. Here, we are targeting rather the area near the San Andreas Fault. And then when we plot this median filtered envelope and have a threshold of 5 times the RMS amplitude of the signal, we see that there are huge number of peaks coming out from the signal. And these are not earthquakes again. These are really signal that that should last at least a few minutes. So when we look in detail at these individual peaks, we see that actually most of them, well, as expected, they have a very strong, in the beamforming plot, when we analyze, go back to the entire array, we see that they have a very strong signal at 6 kilometers per second. This is slowness 1/6, again in the proper azimuth. And when we look at the slant stack trace, we see that effectively, that's what was searching for. It looks like a tremor pattern. This is exactly the location where Asaf Inbal found that this signal were actually not real tremors, but were actually related to train activity. So as scientists, we wanted to check this. So we went in the Coachella Valley, here, essentially at this location. This is the railway. And we actually went about measuring directly the train activity. Very powerful sources. They are equivalent of a magnitude 1 earthquake in terms of radiated seismic energy. That's why we can record them as far as 100 kilometers away from the railway. So knowing this, we again thought of using this source as a repeating source of noise that can be used for seismic interferometry and for monitoring, because this type of signal can be observed both on the array, but also at many stations across the faults. So we computed the cross correlation between this array data and the station, and this is what came up from the cross correlation, the causal side, acausal side, and showing. So this is the array node, the array individual node that within the array cross correlated with FRD. So that's why you have a range of distance here, and you see a clear propagation of a wave here around 5 Hertz, which is actually which has a move out of 6 kilometers per second, which is actually expected from the beam analysis. And then since we know the train source position, well, we don't have timetables, but we can again. We have a good idea of when they travel because we have seismic station close to the railway. We can also make some full waveform computation of the noise cross correlation of this tremor, with the assumption that this tremor radiates essentially body wave, P and S wave, body waves, within a very simple velocity model. And when we do this, we see a very clear match between this synthetic correlation and the observed correlation here in black. So this, what does it mean, this comparison? It actually means that in that case, because of the signal to noise ratio that is pretty low, the scattered wave field propagating, I mean, from this source, from the train source, is not sufficiently strong when it's recorded to actually participate in the full reconstruction of the Green's function. It's not sufficiently strong, meaning that what we end up with is essentially the correlation of ballistic P waves, in that case, that are dominating the tremor signal at long distance. So it's not what we are recovering here. This is not the Green function, and it's actually clearly, from the synthetic analysis, we can understand that it's clearly dominated by the direct correlation of the direct P wave emitted from this train source and recorded at both the station here at the Pinion Flat Observatory and the station across the fault. So since we know that, we can also compute the sensitivity kernel for this P-wave arrival. Sensitivity kernel meaning how much will be affected, how much the structure, so a change of velocity within the structure, will affect the travel time of this arrival here. And this can be mapped here and essentially corresponds to the propagation, again, of a P-wave, a ballistic P-wave traveling within the upper crust. So now we can use these correlations because they are very stable from one train to another. As you can see here, they are very, very stable. We can use this for different applications, and this here, I will go quickly on these slides, but this is one application from Ishao where he was using this train correlation and measuring travel time changes between these train correlation to assess the sensitivity to strain variation associated with solid earth tide. So solid earth tide are permanent changes of the strain within the earth. And one important information that we are lacking is how seismic velocities are sensitive to strain changes. We don't know, actually, and this is very important when in monitoring, when we want from seismic velocity observation to go back to some physical changes of deformation within the crust. So we are using tides, and here this is a typical tidal signal that is recorded at the Pinion Flat Observatory, and each of the red stars shows a train correlation. And so we use those and compute travel time shifts between pairs of correlation. So for high tides, low tides, the RL strain is plotted here, and the time difference of travel time propagation for this peak here of P-wave correlation is plotted here, and you can see a trend. This trend means that there is a clear trend, there is a clear sensitivity of these observation to strain induced by solid earth tide. So what it means is when the earth crust compresses due to, let's say, low tides, velocity will increase, and when the earth dilates, again during high tides, then the velocity will decrease. And so you have you can by plotting the linear regression here, you can have a direct estimate of the velocity strain sensitivity in this case. That is very useful when you do then after monitoring to again relate to physical changes of strain. And this is actually the case that is useful for this type of application here, where Ishao again has been investigating the changes of velocities across 10 years. Because once we have identified this P wave with the array in the cross correlation between the array and one station, you can actually trace back the temporal variations of travel time of this correlated P wave over using permanent station. And here using permanent station on one side of the fault and on the other side of the fault. Here the correlation, you see that they are very stable over many years because the railway doesn't change, the train essentially don't change. And if you measure travel times compared to a reference cross correlation here, you can see that actually there are some very clear changes, and here increase, for example, of travel time of a few milliseconds in 2014. And when you do this cross correlation and travel time variation analysis over many station pairs across the region, you can see that there are both sometimes increase of travel time, and for other stations there are decreases of travel time, meaning that for some station pairs you have decrease of velocity, and for some other station pairs you have an increase of velocity. And this is being interpreted as the effect of a slow slip that was undetected before, of a slow slip occurring on what was thought as being a locked portion of the San Jacinto fault, so that was not supposed to slip. And these velocity changes have been interpreted as being the effect of the strain perturbation induced by this hidden slow slip at the depth of 5 kilometers. So now I will move to another type of observation. And instead of looking towards the trains, this time we'll be targeting the fault, the San Jacinto fault. So we will essentially turn our array to the San Jacinto fault activity and perform the same type of plot. So again, here, this plot is the summarize of the slant stacked at 6 kilometers per second, processed then as an envelope computation and median filter. So here, all the earthquake activity has been removed, which is of course dominating the seismic signals in this azimuth. And we are just focusing on the first main peak that we observe in this median filtered envelope. And this is the type of signal that we get from this peak, this specific day. And you see that there is some, indeed, there is some signal that looks like tremor that lasts hours, and that should be understood. For more details, I'm advertising Quentin's poster right away. He will be showing. I think it's the not this session, but the next session. So if we go back now to our inspect what is this signal in the spectral domain, get more information about this tremor, this specific tremor, to see if it could be some non-volcanic tremor coming from the San Jacinto fault that hasn't been detected before. We are going back to the spectrogram at one node here, and the spectrogram of the slant stack data. And here is the result. So you see that they're actually pretty much different. If I go back and forth, so you see that there are some signals that appear and some signals that disappear between these two spectrograms. For example, in the slant stack spectrogram, you see more vertical lines. So this corresponds actually to very, very small earthquakes that haven't been completely filtered out, and that are seen because they are coherent, very small but still coherent when they are stacked. But also even more interesting, we actually found that this tremor signal was coming from this horizontal line here, around 5 Hertz, that was not seen at all in the single station. So that was the main purpose of the discussion initially, that this was signal that was hidden within one station that could not be seen, and that was only detected by slant stacking. That's by slant stacking of an array. When we perform even more detailed processing within this frequency band, which is adding essentially, 1 bit normalized, we did that, but also adding phase-weighted slant stack to emphasize the coherent energy coming from this data. We're actually able to remove completely what was the earthquake in that case, and even remove also all the signal increased tremor activity, I mean not tremor, but background noise that was during the day, because this part was during the day and this is during the night actually. So we completely reduced the non-coherent energy and finally come up with this this very clear line signal, very weird spectral pattern. And now we are trying to see if this comes from the fault. So first, we are looking at other stations across Southern California. So these are all the permanent seismic station here. This is San Diego, this is Los Angeles here. So we have a variety of broadband seismic stations. And interestingly, you see by eye, I guess, you can find this specific pattern in this time in the permanent seismic station. So actually, you can see it on the broadband permanent station for some of them, and you can find this pattern. Sometimes it's hidden within the noise, but you can still trace it back. And it's actually even stronger in the south part of the network. We are here, which shows that actually it's not related to the San Jacinto fault, because it's stronger at stations that are much farther distance from the fault. So this is a kind of intriguing observation. So we are interested in locating the source of tremor. So we go back to the beamforming analysis of this the signal around 5.2 hertz, and when we compute the beamforming plot, we confirm. I mean, we were looking in that direction, so it's normal that actually we find a spot in that direction. But we confirm that there is indeed a spot at high velocity, 6 kilometers per second, pointing towards the southwest. And this also confirms the fact that we see most of this, the strongest energy on this station. So we have very few information about this type of this origin of this signal. It has never been observed before. The only observation that we have is from Catherine in UCSD, is an earthquake in Hawaii that generated P waves. So the earthquake generated acoustic waves in the SOFAR channel. This traveled thousands of kilometers through the coast of California and then was transferred as a seismic wave. And what Catherine found is that in this region, these T wave convert as P waves with similar characteristic as what we observe, 5 kilometers per second coming from the same azimuth. This is the only, and it's very different from the eastern coast of the US, where the T waves, they convert mostly as surface waves due to the topography of the ocean bottom in the east coast of the US. Here you have a very steep slope here, the ocean bottom, which generates conversion from acoustic to directly P wave. So that's the only information we have. So it is likely, and there are also some hints that the spectral signature is actually also the SOFAR propagation in the SOFAR channel also alters the spectrum of the signal and also creates some peaks in frequency. So it's possible that it's another marker for a possible propagation in the SOFAR channel. But then it's not helping us a lot, because the signal in the SOFAR channel, they have been shown to propagate through thousands of kilometers. So actually this source for this signal can be very far away, since it should be very strong, because the only seismic T wave that has been observed in the past, meaning T wave, acoustic wave transferred as a seismic wave, the only observation that we have is for earthquakes. There is no observation of that type for tremor type signal, to be the first one. Because, as I say, we can observe when we know actually what to look at exactly, we can trace back this type of signal on past data on the permanent stations. We actually found, and also because we have the chance to have a small, an array of station, much less station than the fault scan array, but still an array of station at the Pinion Flat Observatory that has been running for 10 years. We can perform this array analysis over the PY array, same, and also look at permanent station in the region. And what we find is that actually there were other episodes very similar in the past when we look at the last 10 years. So there's one here, and these two stations are very much different locations. So this one is they are like almost 80 kilometers apart. So this is more to the border of Mexico, and this is more north of San Diego. So this is close to the border of Mexico, this one in the north. And you see that still they record the signal. Some of the signal can also be recorded here at this station on this island. It's not shown here. So this is another one. This is the strongest one that we observe. Again, it's another year. And again here, another one with different shape. It's mostly detected during the night because, of course, on permanent station, we cannot reduce the effect of the day activity, anthropogenic activity. And so we miss probably all the events during the day. That's why we only see them during the night. So we are now performing the full catalog for these events, and we still have no idea of the origin, what it can be. So if you have any idea, let us know. One possible is a submarine undetected. I mean, there is no report of actually volcanic activity during the time period we observe these tremors, but it could be far away submarine volcanic activity. Eventually, it will be very surprising, but it could be again acoustic tremor generated by rubbing icebergs, so icebergs breaking and sliding one among the other. This has been observed as acoustic data in the ocean, but never as transferred as seismic acoustic data on the. So it would be surprising. It could be also, and this we are checking. Actually, Dan might have some new information about that, but it could be also oil and gas exploration in the region, where they will shoot air guns for hours like this, and this will actually be recorded on land as a tremor, as a specific frequency. And actually, the lowest peak frequency of these air guns is actually going down to 4.5 Hertz. So it could also match. But this information is public, so we should be eventually be able to assess that more in detail. So thank you. I'd like to finish by saying that we are looking for a postdoc starting September. And if you come working with us, there is a high chance that you will end up shoveling like here on this picture. So just to let you know. Thank you.